your introduction, and let me also start by thanking the organizers, in particular Professor Genser, for pressing me to give a talk, because I first thought that to organize a session is enough to come here, but he suggested otherwise. So that's how I happen to give a talk. And so you see the title of the talk. Now I am representing not only Karlsruhe Institute of Technology, but also Institute in Moscow and the Higher School of Economics also in Moscow. And you see the two of these institutions. So now the work I'm presenting is done in collaboration with Dima Golubev, who is at Aalto University in Finland. And yeah, so that's sorry, that's the thing I'm going to present. I mean, this is an outline. So actually, the title, specific title of my talk concerns mainly the last part of it, but I feel that the issue deserves some extended introduction, which I'm going to give now. Okay, so if we have a scatter, a piece of normal metal, for instance, and we have an incident electron with some transmission probability between 0 and 1, it can pass this scatter in some conducting channel. Okay, so this is transit. Why is that? Okay, so now the famous conductance formula, if you want to calculate the conductance out of this information. So here you are. This is a Landauer formula. You have to sum all these transmission probabilities. Now, obviously, if there is a transmission probability with Tn, there is also refraction probability in this, which equals to this value. And this uncertainty that electron can be transmitted or reflected, it gives rise to fluctuations of the current or to short noise. And this is the famous Hluss formula, which tells you that these fluctuations will occur always as long as transmission probabilities are neither 0 nor 1. Okay? Because in those cases, there are no uncertainty. Right, so this is well known to all of you, of course. Now, what happens if we have, instead of the normal scatter, we have superconductor, then we have incident electron with energy smaller than superconducting gap. Then, of course, we also all know what happens. It does Andreev reflection, so Cooper pair drops into condensate, and hole goes in the opposite direction. And this process can also be described in the spirit of this Landauer formula, but now for this somewhat more complicated system. And this was done by Blonder, Tinkham, and Klapwijk. So this process gives rise to so-called Andreev conductance. Here is it. And it depends on Andreev transmissions in the same way as Landauer formula on normal transmissions. And these Andreev transmissions are related to normal transmissions of conducting channel by this simple formula. Okay. Now, the same way there appear fluctuations of the current in this system, as was shown in the work of de Jong and Benacker. Now it looks pretty much the same as in the normal case, except here you have, of course, Andreev transmissions, and this is a Fano factor, which is called Fano factor. And the elementary charge is double electron charge, twice the electron charge, obviously, because Cooper pairs are involved. Okay, so this was a temperature and zero frequency. Now you can generalize this formula and write down complete formula at all frequencies and all voltages and all temperatures. But anyway, it reduces to those previous results. Okay, good. Now, so once again, I mean, loosely speaking, what is Andreev reflection is that two electrons come from superconductor, come from normal metal into superconductor, form a Cooper pair, which drops into condensate, and this is the mechanism of charge transfer in such a... Now, obviously, it is not necessary for these two electrons be in the same normal metal, which is attached to superconductor. One can also think about this process, that one electron comes from one superconductor, another electron comes from another superconductor, and they are divided by a narrow piece, normal metal, sorry. One comes from normal metal, second normal metal, and here is the superconductor, which is narrow enough as compared to its coherence length. So it's smaller or of order of coherence length. And then the same process can happen. I mean, these two electrons can form a Cooper pair and drop into condensate. Or the reverse process can happen, that Cooper pair gets split into two electrons which go into two normal metals. And this is called Cooper pair splitting. As a result of this phenomenon, electrons in two normal metals, which are separated in space, remain entangled. They are entangled, although they are normal and they belong to different metals. All right, so this is a fundamentally important phenomenon, which is thought to be perhaps useful for this quantum information business, but this I don't want to enter that much. Rather, I would like to discuss the issue how this phenomenon can be identified or measured in experiment. What is it here? Anyway, phenomenon which is called Cooper pair splitting or cross-Andreev reflection, that is two electrons form a Cooper pair coming from two normal metals in a superconductor. Now, we can think of such kind of a device which allows us to pass, here we apply voltages and we can pass current and we can measure local resistance and non-local resistance, cross resistance, and cross conductance in this device. This cross-Andreev reflection called elastic co-tunneling, although this is a bit more complicated than just tunneling process, but in the limit of small transmission, it is, of course, tunneling process. So in any case, this is a simpler process. It's just the electron goes through a superconductor, considering it as a potential barrier. Yeah? So it goes directly from one normal metal to another through superconductor under the barrier. And if we calculate, so why is this? I mean, there should be another formula here, but okay. So, I mean, what is G12 is the cross conductance. So you can apply, let's say, voltages to voltages here. You can measure currents, and you can measure the current response in this terminal 2 response on the voltage V1. And this will be the conductance. This will give rise to conductance G12. So it's a cross conductance. There are local conductances here and non-local this one. This was on that slide, but unfortunately didn't reproduce properly. I mean, I had this formula. But anyway, the point is that in the tunneling limit at 0 temperature, these two processes give exactly the contribution to this non-local conductance, but with a different sign. And it was shown by these people some 20 years ago that actually these two contributions cancel exactly, and so you can hardly then identify this cross-Andreev reflection contribution in such an experiment. Now, you can go beyond the tunneling limit and consider, let's say, large transmission, let's say full transmission of these NS barriers. And that we did with Misha Kolenkov also quite some years ago, and he's in the audience, by the way. What we have shown that in ballistic structures where you have full transmission, you have no cross-Andreev reflection contribution to non-local conductance. Yeah, at full transmission, it doesn't exist. So again, bad luck in the sense that you cannot identify it. And okay, and then yet one more limit, which is pretty important one, is that I mean, you can have arbitrary transmission and disordered system, which is probably the closest situation to real experiment. And in that case, you can calculate, let's say, this, you invert the conductance matrix and you calculate the cross resistance. And in this case, you find a very funny at the first sight result that actually this cross resistance does not depend on anything except for, I mean, this x1 and x2 is these 2 points, so it's a distance between these two terminals, I mean, the length of this superconducting wire here. So as long as it is shorter than a coherence length, then you can drop this, and then the cross resistance depends only on the normal state resistance of this wire here between these two. No, sorry, not between these two, but at the length, at the segment of length of order psi here. Yeah, so this is some kind of universal result. It doesn't depend on the transmission, nothing. Yeah. And in fact, it was supported by several experimental results, but I also don't want to go deep into this subject. I just want to mention that also in this case, you're not going to extract contribution from cross-Andreev reflection we are interested in, okay? And so the basic conclusion out of this is that if you are going to make non-local resistance or conductance measurements, you have slim chances to basically to study this cross-Andreev reflection separately from other processes and extract processes. However, there is another way to get extra information from this system. Namely, you can consider noise, namely short noise. You can consider current correlation function of that form. And what it includes both local noise, current noise, and non-local current noise. And in particular, since we are interested in this cross-Andreev reflection process, we are going to study this non-local contribution, which means that you have, for instance, r equal to 1 and r prime equal to 2. You have a correlation between currents in going into the first terminal and the second terminal. Now, in this case, normal do not involve superconductivity. Then it is well known as a kind of theorem that noise is always negative. And this has to do with the principle. So it's quite fundamental result. However, in the system which involves superconductivity, the situation might be in principle, this cross-correlated short noise can turn positive, and this is due to cross-Andreev reflection process. Okay. And this fact we are going to so make use of in order to identify this cross-Andreev reflection process. Okay, in fact, the first step was done by these people quite some time ago, who calculated this cross-correlated short noise in the tunneling limit, when NS junctions are tunnel barriers. Both junctions are tunnel barriers, so you can proceed perturbatively. Then you recover such kind of a contribution. So it's VA and VB is the same as V1 and V2 here. And so you can show that your cross-correlated short noise consists of two contributions. One is cross-Andreev, and another is elastic co-tunneling. So they're represented here. And you see that now you can, by changing bias voltages, VA and VB, you can play with the sign of this total formula, making it either negative or positive. And if this cross-Andreev reflection contribution dominates, then you have a positive sign. And in fact, there was an experiment in the group of Venkat Chandrasekhar who demonstrated exactly this. So this is theory, and this is experiment. So you see this positive cross-correlated short noise, which is indication of cross-Andreev reflection. All right. Now, what we somehow wanted to do is to go to explore this issue beyond the tunneling limit, in which case you have, in fact, many more possibilities, meaning that you can have different transmission distribution. Not transmissions are small, and the question is how this fact would influence the whole picture of this cross-correlated short noise. Okay, so the model is written here, so it's pretty simple and general, in fact. So you have two normal metals, two terminals, normal terminals, attached to superconductor, or one superconducting electrode via junctions with arbitrary transmissions and arbitrary transmission distributions. So it's very general. Now also, and this I will need in the end of my talk, you can apply not only different voltages, but you can apply different temperatures. So in fact, you keep these two terminals at different temperatures, making this whole thing even more non-equilibrium as compared to the limit when these temperatures are the same. Okay, so what you have is two parts of the Hamiltonian describing normal metals. You have also part of the Hamiltonian describing superconducting terminal, and you have extra terms responsible for transmission of electrons between normal and superconducting terminals. So it's very general, okay? Now, what we need to know is, in fact, this function, which is called generating function, and this function is related in such a way to the probability for N1 and N2 electrons being transmitted between normal terminal 1 and 2 and superconducting terminal during time t, okay? Now, this is the definition of this generating function. Now, if you, what is the use of it? For instance, if you know it, then you can easily recover, in principle, all current correlation functions, but we need only the first two, so the current, and then you just take the derivative with respect to this counting field. This chi1 and chi2 are two counting fields. And now if you want to calculate, to recover noise, in particular non-local noise, as in our case, then you just take the second derivative, and then you are done. Yeah? You can proceed further and also recover higher moments of the current, but that we don't need today. Okay, so now, in fact, it's quite a problem theoretically to evaluate this thing, but fortunately, making use of Keldysh technique and path integral technique, you can do it. So I completely skip this part because it's pretty technical. In any case, you can exactly evaluate this generating function in such a form where this matrix consists of each of these elements of this matrix is 4x4 matrix itself, and it corresponds to Keldysh-Green functions of the first terminal, of the second normal terminal, of superconducting terminal, and this is the matrix T, which describes transfer of electrons between terminals, and it also depends on these counting fields. This is formally the exact result. It also, these functions, they also contain all information about distribution function of electrons, temperature, okay, and so on. Yeah, so this is a general result. Now, if you go and evaluate it, you end up such an expression. I show it for you not to digest it, but just to show that it's some work which has been done, and if we want to define symbols, it will be yet one or two transparencies, but that I skip because it makes little sense to discuss it in that form. Rather, I flash one result which we obtained some time ago, is that at full transmission frequency limit, this complicated formula gives a very simple result like this, and it shows that at zero temperature we have only positive cross correlation due to cross-Andreev reflection at zero temperature. Okay, so this is the way how we can visualize this cross-Andreev reflection and Cooper pair splitting, which yields this picture of entangled electrons in different metals by calculating this noise. So the message is that by increasing transmission, you essentially increase, making it large, you increase the contribution of cross-Andreev reflection to non-local noise, and actually the other contributions die out in the limit of full transmissions. Okay, so you can calculate, of course, different transmissions. So here are the results which I just plotted for you in such a form. So you have this nice looking pictures in different limits. So it's a tunneling limit, which I in the beginning. Then it's this good contact limit, which essentially is determined by cross-Andreev reflection. And this is another important limit of diffusive contacts, okay, which you have an experiment where you have this nice picture with all these red parts showing that cross-Andreev reflection dominate in these parts. All right. So and now finally I came to the most recent issue which I want to convey is that yet another tool how to control the relative contribution of cross-Andreev reflection to non-local noise is to apply a temperature gradient. And the idea goes back to the work of these people who got actually Nature with this, who considered just atomic scale junctions, normal junctions, and demonstrated that if you apply temperature gradient, you get an excess noise, excess short noise, it's written here, which is proportional to the square of this temperature gradient, of this delta T. Okay, so here is, in fact, they made an experiment and showed that actually it's parabolic here. So we apply the same idea now to non-local noise. And then, in fact, this general formula which I showed you, it also includes this situation. So any temperature gradient is allowed. And in the limit of small voltages and temperatures as compared to critical temperature of a superconductor or to other parameters, we can, in fact, recover pretty simple formulas which I'm going to show you. Now, it turns out that if we introduce some effective temperature, which depends on temperature, which is just average between these two temperatures, and this delta T, which is just temperature difference, then expressing our result, theoretical result, in terms of this effective temperature, we can actually get very simple formulas which describe all important cases. So for instance, if we consider a zero bias voltage limit, then we get to this excess noise, which is due to this delta T, this temperature gradient. And in fact, it turns out that at maximum, this excess noise is not at all small. It's comparable to the total noise. It's still a bit smaller, but it's of the same order, let's say. And this maximum occurs at delta T equals to T. But you can also then go to non-zero voltages, and then the result will essentially depend again, as before, on emission distribution. So in the tunnel limit, it's remarkable to get formal cases. And I'm not sure if it's visible, but this excess noise shows up here as compared. So this is zero temperature. This is finite temperature, but no temperature gradient. And here you have temperature gradient. So you see a bit of a difference, maybe in this case, not really. It actually, okay, so the colors are a bit different my computer. But anyway, so what you see here is fully transparent barriers. So at zero temperature, you see it's almost always red here at zero temperature. And then this blue part, which is negative cross-correlated short noise appears and expands. And here you see a bit of a difference, but the colors, as I said, are a bit different. I mean, you can notice, but if you have temperature gradients, so it's still somewhat different. And then finally, this diffusive, this explicit formula, and you see that the pattern is different depending on whether you have zero temperature, finite temperature, or temperature gradient. So what we've got this explicit description, theoretical description with all this relatively simple formulas describing this cross-correlated short noise. And this gives us an extra tool to control this cross-Andreev reflection contribution to non-local short noise in this hybrid, in a sense, structure. So I leave you with some conclusions. Thank you for your attention.
Thank you very much, Dr. Zaikin. Is there any question? Yeah, here.
Okay, thank you. Thank you for very nice and clear presentation, and 2 short questions. In your path integral stage, is the action quadratic Gaussian or not? If not, then how do you treat path integral?
Well, look, I mean, of course, it's not quadratic because it's superconducting, but you do Hubbard-Stratonovich transformation, and then you basically express it in terms of fluctuating fields. Yeah, so you effectively make it quadratic in electronic degrees of freedom, and then you can sort of integrate them out exactly. But you are left with fluctuating fields, and then you have to do some approximations. But
Yeah.
But this is pretty
Good.
standard.
And second short question, how to measure it? Have somebody already measured this nice noise, or you are planning to do this? Thank you.
Yeah, I mean, this is a good question because, you know, this big formula which I showed, in fact, showed very nice agreement with experiments of some people already done quite some years ago. For some reason unknown to us, until now, they didn't publish it. So the answer to your question is yes, we are aware of such. There are also other experiments, but not that nice as those experiments. But we wanted even maybe to collaborate and to write a joint paper. For some reason, either they went to some other field or not. I mean, that's the situation. But our motivation in part was to explain their experiments because it was done even before we derived this. So we have published, they did not. Okay.
Thank you.
Yeah, so to what extent you are treating non-equilibrium dynamics of quasi-particles in your structure? So
What do you mean, to what extent?
I mean, there are various possible non-equilibrium states associated with quasi-particle states. So does your approach account for that, or?
Of course, it accounts for everything.
Okay.
Any question? I want to question.
Yeah.
In a few previous page, there are superconducting part, and there are two.
Which one?
Voltage 1, voltage 2.
Ah, you want this one?
Yeah.
Okay.
This is also the experiment also like that.
Right. Yeah.
So all the solution has no any time parameter. So for example, in the experiment, so you need the time.
Yeah.
So is there any time dependent solution?
Yeah. Of course. I mean, this is.
Immediate time, right?
Yeah. I mean, we are calculating correlation function. It depends on time difference or on frequency. Okay.
Yeah.
And this is your time. I mean, so it explicitly depends. I mean, you can say on energy or on frequency or on time in the time domain. So I mean, I can.
Like a discrete.
Oops.
Solution.
What is this? Okay. So I just want to show you the initial formula which we sort of deal with. Yeah. Okay. So here you see. Yeah. You see this time here. Yeah. So.
Okay.
Yeah. Okay.
Any question? Okay. I would like to thank you your presentation.
Thank you.